Hey everybody, in this video we are going to be talking about intermolecular and intramolecular forces. Now, an intermolecular force is a force that occurs between molecules, and inter just means between. And the different intermolecular forces we will look at in this video will be London dispersion forces, Dipole-Induced Dipole forces, Ion-Induced Dipole forces, Dipole-Dipole forces, hydrogen bonding, and Ion-Dipole forces. Now let's talk about the intramolecular forces. Intra simply means in, and when I say intramolecular forces, I mean between the atoms in molecules, metals, ions, and etc. So for example, we have metallic bonds, which we will learn about soon, covalent bonds, which we have already learned about, it's just the bonds between atoms, and an ionic bond, which is a bond between a cation and an anion. Now, intermolecular forces keep the molecules together as solids and liquids, and sometimes they can contract gases. So for example, if you have a gas that has high intermolecular forces, or IMF, then the gas will be attracted to each other and it will contract and become a gas with a lower volume. Now, the intramolecular forces are the forces that keep the atoms and ions of metals, covalent molecules, and salts from falling apart. And this makes sense because, for example, the covalent bond keeps these two atoms from falling apart. For example, O2 has a double bond to keep the two oxygen atoms from falling apart. And note that strength generally increases down the list. So as you increase down this list or this list, the strength of the bond generally increases. And let's read on. All these forces are related to electrostatic forces, and electrostatic forces in this case are the attractions between positive and negative charges. So because electric charges are involved, Coulomb's law will be important, and Coulomb's law will state that a larger charge means more attraction, and the smaller the distance between charges, that's also more attraction. So keep a note of these two factors, along with a few other factors, as you look at these types of forces and what makes them strong or weak. So without further ado, let's begin. The first force we will look at is the London dispersion forces, or LDF. This is a force that exists between all molecular substances, and by that I mean both polar and non-polar. So basically all molecular substances display London dispersion forces. At any given instant, any part of an electron cloud can be more dense in electrons than other parts, and this imbalance of electron distribution creates partially positive and partially negative ends called temporary dipoles. So in this example, you have a cloud, and there's a higher electron density on the right side than the left side at any given instant because electrons move around randomly and nobody's perfect. So, because of the randomness of the movement of these electrons, sometimes electrons can build up on perhaps one side of an electron cloud and be deficient on the other side. And because of that, this side will have a higher electron density, and that's why this side has a partially negative charge, while the left side has a partially positive charge. Now, if you don't understand why this occurs, you can watch the video about polarity that I made, which does a very good job at explaining why one side of an electron cloud might be partially negative or partially positive. And yeah, now why is LDF considered an intermolecular force? Well, as we just learned, any molecular substance can create temporary dipoles where the electron cloud of the molecule can have a partially negative end and a partially positive end. And because of this, perhaps maybe a partially negative end of an electron cloud that has deformed may attract a partially positive end of another molecule, perhaps another I2 molecule. And if you remember, negative charges and positive charges attract each other. So as a result, these two molecules will attract each other. And this red dotted line just represents kind of an intermolecular force being created between the two. And this intermolecular force kind of keeps these two molecules together. Now let's read this note that I wrote. These are temporary dipoles and they don't last forever, so that's why they're usually weak. However, the more electrons there are and the more dispersed the electrons are, and electrons farther away from the nucleus tend to be more dispersed, the more easily they can disperse to form temporary dipoles since they are not as close to the nucleus and are free to move around the molecule. So if electrons are not as bound to the nucleus, then they tend to be freer and they tend to have more freedom to move around the electron cloud, and because of that, deformities are more common, which causes these partially negative and partially positive ends. Now, more electrons and more dispersion allows stronger and more frequent temporary dipoles, since if electrons are more dispersed, they can move around more easily and create distortions that create more of these partially positive and negative ends of an electron cloud, and this result creates stronger LDF forces. So, if more electrons means more LDF, that means that a higher molar mass, which typically means more electrons, correlates to stronger LDF forces. So let's take an example and let's compare iodine solid and NH3 gas. Now we have to compare the number of electrons. So I2 has 106 electrons, NH3 has 10 electrons, and the molar mass of I2 is 253.81 grams per mole. The molar mass of NH3 is 17.04 grams per mole. And because I2 has more electrons, and these electrons are located farther from the nucleus, they can easily disperse and more easily create distortions in the electron cloud, which creates partially positive and partially negative ends on the electron cloud, which leads to LDF. So, because I2 clearly can do this more easily, then I2 will have stronger London dispersion forces, while NH3, ammonia, will have weaker London dispersion forces. Now let's take a look at the next force. So we have something called Dipole-Induced Dipole forces. So weird name, let's find out what it means. A molecule with a net dipole, or in other words, a polar molecule, induces or forces a nonpolar molecule to have a temporary dipole. So, instead of being all natural and having a temporary dipole as we did before, where it was all random, this time it is induced or forced upon by a polar molecule. So, for example, HCl gas is a polar molecule, and at first these two will interact with each other, and I2 is nonpolar, and the electrons on the left side of this I2 molecule will kind of say, let's move away from that partially negative Cl atom, because this Cl atom is partially negative due to polarity, and these electrons on the left side do not want to be near that partially negative end because electrons are negatively charged, so naturally they will move toward the right side, and because of that, the left side is now partially positive due to the absence of electrons, and the right side is partially negative due to the excess of electron density. And because of this, HCl will have succeeded in creating an induced dipole on this I2 molecule. And as you can see, the partially negative end and the partially positive end attract each other, and thus forces called the dipole-induced dipole forces form between these two, and this force keeps these two molecules together and attracts both of them to each other. Now, how can we make stronger dipole-induced dipole forces? Well, you can either have more polar molecules, or you can have nonpolar molecules with higher molar masses. And the reason why high molar masses corresponds to stronger LDF is because high molar masses typically means more electrons. And both of these factors can contribute to a stronger dipole-induced dipole force. Now, I wanted to point out a misconception. When you want to explain why I2 has a stronger LDF than NH3, you can't simply say that this has a higher molar mass than this, because molar mass is just a trend that correlates with LDF. It is not an explanation. It is not a means to an end. Instead, you have to explain why the LDF forces for I2 are stronger in terms of electrons and how many there are, and how more dispersed electrons means that there could be more frequent distortions in the electron clouds, which means more frequent partially positive and partially negative ends on the electron cloud. And all of this contributes to a stronger LDF for I2 over NH3. So remember, intermolecular forces and intramolecular forces are caused by electrostatic forces, so you have to talk about these in terms of electrons, protons, whatever that may be. And yeah, that's just a point I wanted to make. So let's move on and talk about the ion-induced dipole. Now, this is very similar to the dipole-induced dipole, but this time, instead of it being a polar molecule, this time an ion, typically dissolved in water or any solvent, induces or forces a nonpolar molecule to have a temporary dipole. So this Na plus is positively charged, and the electrons on the right side might say, I want to be near that Na plus, and they will be attracted to it, and because of it, the electron density will move toward the left, and because of that, this side will be partially negative, this side will be partially positive, and you just created a little linkage, and that is called an ion-induced dipole force, and I should add force to be more specific, because this is an attractive force that keeps these two things together. So it also works for anions, but for anions, of course, since this is negatively charged, this side should be partially positively charged. And you can think of these as just maybe a bond, albeit a weak bond, or you could think of it as an attractive force. And this attractive force is more accurate because it describes these two being attracted to each other. So you could think of it in either way, and both of them work because, as you'll see later on, a covalent bond is simply just an attractive force between two atoms due to the electrons they share. So let's read about how an ion-induced dipole force can increase in strength. Now, ions with a higher charge or smaller radius, and know that this is Coulomb's law, and nonpolar molecules with a higher molar mass typically make for stronger ion-induced dipole forces. So let's move on to our fourth force, our dipole-dipole forces. Now, these are attractive forces between two polar molecules, and remember, polar molecules are molecules with a net dipole moment. These polar molecules have permanent dipoles, so not temporary, but permanent, because the net dipole moments on polar molecules always exist. Only molecules with a net dipole moment can form dipole-dipole interactions between atoms. So in this example, we have HCl and water, and both of these are polar molecules. So notice how the H is partially positive, and the Cl is partially negative, and thus the Cl can be attracted to these two partially positive negatively charged H's, and this creates an attractive force known as a dipole-dipole force. Now, as you can see, a net dipole exists on both of these compounds, and as a result, you can create dipole-dipole forces between them. Now, let's talk about molecules that have bond dipoles but no net dipole, such as CO2. So, if you recall, a bond dipole is just the dipole between two atoms, and the net dipole is, of course, the overall dipole when you add up all the bond dipoles. So, first off, CO2 has bond dipoles here and here, but the bond dipoles cancel out, and thus there's no net dipole for CO2, and because of that, we know that it's nonpolar. Since dipole-dipole forces only form between atoms of molecules with a net dipole, and since CO2 doesn't have this, then CO2 will not have dipole-dipole forces. Now, you might draw it out and you might say, oh, partially negative, partially positive, high electron density, low electron density. Hey, we might be able to form some dipole-dipole forces here, but no way. You might think that this might form, where the partially negative oxygen might be attracted to the partially positive carbon, but typically this does not happen because there's no net dipole in either of them. And it's kind of weird, but let's read on. Since dipole-dipole forces can only form when both molecules have net dipoles, and since CO2 doesn't have that, then it cannot form dipole-dipole interactions with other CO2 molecules. The reason for this is because without a net dipole, CO2 has a much harder time making these dipole-dipole forces, such as between the partially positive C and the partially negative O. Therefore, nonpolar molecules like CO2 simply don't make dipole-dipole interactions very easily, or even at all. And I know this is a very simple explanation, and it's much more complicated, but even I don't understand how it works, and let's just leave it at that. Let's just leave it at the fact that nonpolar molecules cannot form dipole-dipole forces, and that dipole-dipole forces can only form between two polar molecules. So just remember that. And how do you make these dipole-dipole forces stronger? Well, the more polar molecules are, makes the dipole-dipole forces stronger. And this is because stronger polarity, which means maybe this is more partially negative than normal because maybe it's more electronegative, then a higher partial charge means stronger forces, since at the beginning, if you remember, Coulomb's law stated that the larger the magnitude of the charge, the stronger the attraction. So let's move on to the next intermolecular force. This intermolecular force is known as hydrogen bonding. And I don't know why my screen just went down like that, but let's continue. An attractive force that forms between an H attached to an FO or N and a lone pair of FO or N. So in this example, we can see that there's water, which has an H attached to an O, and a lone pair of FO or N, and in this case, it's another water molecule, so that's an O, and it's a lone pair of an O, and there's an attraction between the H attached to the O and the lone pair attached to the O. And they are attracted because obviously this lone pair is negatively charged and this is partially positively charged. Now let's talk about why hydrogen bonds form and how it differs from dipole-dipole. So these H's are more partially positive than usual because the OH bond is very polar. H is also very small, so it can get close to the lone pair on the O. So in this case, instead of atom being attracted to atom, the atom is attracted to the lone pair. So that's what makes it different from dipole-dipole forces. Now, what about the O? Well, the O is more partially negative than usual because the OH bond is very polar. In addition, the lone pair has not partially, but fully negative charges. So instead of being maybe a fraction of -1, it is instead fully negatively charged, and in this case, each lone pair has two -1 charges from two electrons, So as you can see, these lone pairs are not typically partially negatively charged. They typically have a charge of -1 or greater, and because of that, the hydrogen bond is especially strong since the magnitude of the negative charge is quite high, especially for something like a lone pair, which has literally 2 electrons in them. So let's draw these hydrogen bonds, and we drew one for water where the H is attracted to the lone pair of the O. Now what about for HF? Well, remember, an H attached to an F, O, or N will allow for hydrogen bonding, and the lone pair attached to the F, O, or N also allows for that. And they both have to concurrently happen at the same time for an H bond to form. So, in this example, we have 2 hydrogen fluoride molecules, and the lone pair on the F is attracted to the partially positive H that is attached to an F. So we basically met the criteria for a hydrogen bond where the H has to be attached to an FO or N, and a lone pair has to be attached to an FO or N. So mission success, and now let's read on. A hydrogen bond between H or F is strongest since F is the most electronegative. Next comes O and then N. So again, the charges or the electronegativities matter because F is the most electronegative atom, and because of that, it is able to have a really powerful partially negative end. And remember, the higher the magnitude of the negative charge or the positive charge, the stronger the attractive forces are. So that's why F has the strongest hydrogen bonding out of the 3 possible choices. Now, let's talk about why Cl cannot form hydrogen bonds even though it has a similar electronegativity to oxygen or nitrogen. Now, the lone pairs on the Cl cannot form hydrogen bonds because the electron cloud of Cl is too large and the electrons are too dispersed for the lone pair to properly form an H bond with an H covalently attached to an F, O, or N. So that's why Cl cannot form hydrogen bonds. Now let's talk about our next intermolecular force. This one's the strongest one. These types of forces are called Ion-Dipole forces, and they are forces, or you could think of them as bonds, formed between a polar molecule, which has a net dipole, and an ion. So again, it's the strongest intermolecular force, and it happens in aqueous solutions and in hydrates. So an Na plus cation in solution can interact with water molecules around it, and water molecules have a partially negative end on the oxygen, and these ends can attract or be attracted to the positively charged Na plus. And the reason why this is the strongest is because look at that. The Na plus is a whole +1 charge. It's not partially plus, it's fully plus. And because of that, a larger magnitude in electric charge means a stronger intermolecular force. And you see multiple waters surround the Na plus. It's not just one. There could be another one here that's attracted to the Na plus. Now, what about our Cl minus? Well, the Cl minus will attract the partially positive ends of the water molecule, which are the hydrogen atoms, and this happens many times with many water molecules, as you can see here. And this is the reason why salts dissolve in water, since as you can see, water molecules surround Na and Cl and kind of separate them. And to learn more, check out my solubility video. Now, how do you make these ion-dipole forces stronger? Well, a higher charge on the cation or anion, or a smaller ionic radius for the ion, or a more polar molecule, tends to make these ion-dipole forces stronger. So again, borrowing the ideas of Coulomb's law. Now let's move on to our intramolecular forces. The first one we will look at is the metallic bond. This is generally the weakest intramolecular force. In a metallic bond, there are a sea of valence electrons separated from the nucleus of the metallic atoms. and these valence electrons are usually s and p electrons, but the d electrons in transition metals can also be used as valence electrons. And what I mean by s, p, and d electrons, I mean the outermost, which is why they're called valence electrons. Now, these C of electrons hold all the atoms together because, as you can see, the Zn, once it loses its electrons, it's going to become Zn2+, and these electrons that are moving around are the delocalized electrons, or our C of valence electrons, and these electrons make metallic bonds between, Zn atoms, and this is what keeps everything together. It's kind of like a spider web. And these C of electrons hold everything together and allow electricity to pass through, which is why metals conduct electricity. So an electron might hop by and be able to move around freely because, the electrons are in a C, and in a C, water can move freely. So you can think of it that way if you want. Now, there are other properties caused by metallic bonding. We have thermal conductivity, which means that the metals can transfer heat through itself easily. We have ductility and malleability. And ductility basically means you can turn metal into thin wires, and malleability means that you can deform metal and it will still stay as a solid, or it will stay together as one piece. Now, the reason for this is that you can deform metals because metal atoms simply move aside in the sea of electrons as if someone pushed aside a ball through water. So because metal atoms simply just move aside, you can simply deform them, and that's why they're malleable. So metallic bonding also results in the luster, or the shine, of metals. It also results in the insolubility of metals, which will be discussed in the next unit. Now, we have something known as an amalgam. Now, amalgams occur when liquid mercury dissolves other metals, since things with similar properties can dissolve each other, and this will also be discussed in further detail in the next unit. Now, how do you make metallic bonds stronger? Well, a smaller metallic radius, or maybe a higher charge, or maybe more valence electrons, contributes to a stronger metallic bond. So this means transition metals typically have very strong metallic bonds since they have d valence electrons, and these are a lot of electrons, so it creates a bigger sea of electrons and creates more attractive forces, and that means more metallic bonds, and that means stronger metallic bonds. And remember, a metallic bond simply refers to the attraction between the cations and the electrons surrounding them. So the more electrons you have, the stronger the metallic bond you will have. So yeah, let's move on to our next bond. We have our covalent bond. And as you may know, these are bonds that form when two atoms share electrons. So in this example, you can see that there are attractive forces between the electron that's shared and, the nucleus, which is positively charged. And that electron might be attracted to the positively charged nucleus in the iodine. And it goes many ways, like this way and this way. And in the end, you get a bond. Now you can watch a video on covalent bonds in Unit 5 for more information. So let's read on. Shorter bonds mainly contribute to higher covalent bond strength, as mentioned in that video about covalent bonds. Now, bond length has to do with whether it is a single, double, or triple bond, as well as the atomic radius of individual atoms. Now, there's something special. Sometimes there can be a network covalent system. This is when atoms are connected by many covalent bonds, and these are called covalent network solids, and they are macromolecules because they are made of lots and lots of atoms, and they seem endless. So in this list, I want to introduce to you some of the compounds that form network covalents. So all of the allotropes of carbon are covalent networks except the ones that end abruptly, such as D, E, and F, since they are spheres and they end abruptly. So your covalent network compounds include diamond, graphite, nanotubes, amorphous carbon, silicon dioxide. and germanium and silicon, and these behave similarly to carbon. So let's talk about our strongest intramolecular force generally. They are called ionic bonds, and these are electrostatic attractions between cations and anions that form ionic compounds or salts. So in this example, we have sodium chloride, and we have two formula units of sodium chloride, and notice how the positively charged cation is attracted to the negatively charged anion, and this occurs 4 times, and that's what makes ionic bonds very strong, not only because it's a short bond, but also because it is fully charged. So you have a fully charged +1 and a fully charged -1, and higher charges means stronger bonds. So these are not partial charges, but they are fully charged, and they are also permanent too. So, I mean, these ionic bonds are very strong. Now, how do you make ionic bonds stronger? Well, you could have higher charges and smaller ionic radii for the ions, and all of this contributes to a stronger ionic bond. So, let's now move on to the next topic. Here's a list reviewing all the forces that we just talked about, and we will now talk about the melting point and boiling point trends for compounds that contain these types of forces. And note that stronger bonds between molecules or ions or even atoms that will be broken during melting and boiling corresponds to a higher melting point or boiling point. So we are going to focus on the bonds that will be broken during melting and boiling, and those will be the forces that we consider when we consider whether it has a high or low melting point. So the forces that don't apply to melting and boiling include dipole-induced, ion-induced, and ion-dipole forces. Now the ones we will be focusing on will be LDF, dipole-dipole, hydrogen bonding, metallic, covalent, and ionic. So keep a lookout for those types of bonds as we go down this list. So this list ranks the types of compounds from the lowest melting/boiling point to the highest melting/boiling point, since these two are really closely related. Now, the first one we will talk about are nonpolar molecules or atoms. Now, all atoms are nonpolar because, as you may know, atoms cannot form bond dipoles, and because of that, they will always be nonpolar. So, nonpolar molecules or atoms only have London dispersion forces at their disposal, and this is a drawing of the LDF forces occurring between two O2 molecules, and these typically have the lowest melting and boiling points, and because they have low boiling points, they are typically gases at room temperature. So as an example, we see that O2 has a melting point of -218.79 degrees Celsius. So that's very, very low. That means that it melts at a super duper low temperature. And the same idea goes for boiling point. O2 will boil at a super duper low temperature. So by the time that reaches room temperature, it will already be a gas. And that's what we observe because O2 is a gas. Now, we have some exceptions, of course. I2, which is nonpolar, is a solid because it has a very high LDF force due to its number of electrons. Now, why didn't I talk about the covalent bonds, since these are super duper strong? But the thing is, when we melt and boil stuff, we only break certain bonds, and in this case, we only break the intermolecular forces in melting and boiling nonpolar molecules or atoms. And this is never completely done because we will always still have some intermolecular forces, but as you melt and boil stuff, a majority of these forces are broken, and generally, when you transition from solid to liquid to gas, these intermolecular forces get weaker and weaker because atoms are getting farther and farther apart. And remember, things that are farther apart means that there's less attraction. Now let's talk about why only intermolecular forces are broken. So for example, when you melt ice, you want to melt the ice so that the particles become dispersed and free moving, so that in the end you have many particles that are moving around in liquids. So for something like water, H2O, all you have to do is break the intermolecular forces between the H2O molecules in order to get them into small individual molecules that can move around freely, and that's all it needs to do to become a liquid, for example. And same thing goes for a gas. If it wants to become a gas, it has to break those weaker intermolecular forces, and once those are broken, you will get a gas. And in the end, you never have to break covalent bonds, because you just have to break the intermolecular forces to get small particles that are capable of moving past each other, which we observe in liquids and solids. So let's talk about the second type of compound. The second type of compound will be polar molecules. Now, I don't know why I wrote atoms, but atoms can never be polar. And polar molecules exhibit LDF, of course. They exhibit dipole-dipole. And some of them, but not all of them, exhibit hydrogen bonding. And since there are more intermolecular forces, these types of molecules will have higher melting and boiling points. And they are typically gases, liquids, and solids at room temperature. So note that everything that I'm talking about, especially regarding the states, is at room temperature. And just like nonpolar molecules, polar molecules have only their intermolecular forces broken during melting and boiling, because when you're becoming a liquid or a gas, all you need are free moving particles, and just by breaking these intermolecular forces, you get these free moving particles. So there's no need to break covalent bonds, which are pretty much hard to break and unnecessary, especially when you're a liquid or a gas. Now, let's see metals. So metals will have the third lowest melting point or boiling point. And these metals have metallic bonds, of course, and they are almost always solids, and the exception is mercury at room temperature. Now, during melting or boiling, metallic bonds are broken, because if you have a piece of metal and the metal has a bunch of metallic bonds, it's just one hunk of metal, and one hunk of metal can't freely float around. So you gotta separate those metal atoms, and separating them involves, of course, heating it up and melting and boiling them. And once you separate these atoms, you effectively break these metallic bonds, and that allows these atoms to move freely around each other, and that's what's responsible for liquid and gaseous metals. So during melting or boiling, the metallic bonds are broken. Now, they are never completely broken, because even in the gaseous state, just like for the first two that we looked at, there will always be some type of attraction between the metal atoms and, the electrons that surround them. And this attraction means that metallic bonds will always exist, even though they might be very weak, or maybe they might be nearly non-existent. Now, I forgot to mention, but let's take a look at the melting point of CH3OH, a polar molecule. Its melting point is negative 97.6 degrees Celsius, which is much higher than the melting point of oxygen, because it has more intermolecular forces. Now, let's look at the melting point of calcium. Calcium is a metal, and it has a melting point of 842 degrees Celsius. That's way higher than negative 97.6 degrees Celsius. Now let's go even higher. Now, ionic compounds or salts have ionic bonds, and these ionic bonds keep these compounds as solids at room temperature, and because of that, if you want a salt to become a liquid, you have to break these ionic bonds in order to get these ions to move freely around. So you have to heat it up and break these ionic bonds in order to get these ions to freely move around as they do in liquids and solids. So during melting or boiling, ionic bonds are broken. Now let's take a look at the melting point of a salt such as, well, actually, let me correct the formula. It's not supposed to be Fe2O, it's supposed to be FeO2. So iron 4 oxide has a melting point of 1,377 degrees Celsius. So that's quite a high temperature. Now let's take a look at the champion of melting and boiling point. These are known as covalent network compounds or solids. So these are always solids because they have such a high melting point, and these have covalent bonds. And why did I write covalent bonds here and not for these guys? Well, for covalent network solids, you have to actually break covalent compounds in order to get it into a liquid or a gas. Now, let's talk about why covalent bonds are broken in melting and boiling. In melting, the liquid consists of freely moving particles, as I mentioned before. For normal covalent compounds, breaking the intermolecular forces are enough to create free-moving particles, but in covalent network compounds, the macromolecule is so large and essentially one particle. Therefore, covalent bonds have to be broken to create free-moving atoms. So, it's going to take much more energy to break covalent bonds, and that's why something like diamond, a covalent network compound, has a melting point of 4,027 degrees Celsius. Now let's talk about comparing melting point and boiling point within a group. When you compare melting/boiling point in a group, consider the forces and compare shared forces by taking a look at what makes those forces strong. For example, if we compare H2 and O2, they both have LDF, but we can compare the LDF forces of H2 and O2 and find out that O2 actually has more electrons that are located farther from the nucleus, and because of that, it has a higher melting and boiling point than H2. And remember, you can consider melting and boiling point as following the same trend when it comes to these inter- and intramolecular forces. So that's all for this video. There is a lot of information in it, and in the next video we will talk more about melting and boiling, and we will do a few practice problems. So thanks for watching, have a nice day.